Okay, this experiment is to let us learn about measurement technique, that is strain gauge technique for measurements of simple loading. And in this case, we're going to learn how to do loading for pure torsion and pure bending. And we will also load in combined loading so that we can learn how torsion affects bending and how bending affects torsion. For this case, we have an experiment in which we have a very simple tube. This is an aluminum tube, and the aluminum tube is supported from both ends. The tube itself is hollow, and the tube has an outer diameter of 1.905 centimeter and an inner diameter of 1.65 centimeter. And to this tube, we are attaching loading arms. You can see that there's a loading arm right here in the center, and there is another loading arm also of the same size, same dimensions, that is welded or attached very rigidly to the back here. This loading arm is 18.82 centimeters from the center. So from here to the loading point is 18.82 centimeters. Okay, so if you look at this tube, we can consider it as a beam, and the beam is supported rigidly from one end. So if you look at this end, the end is attached very rigidly to the frame itself. So there's no flexibility on that end, and therefore if you induce any moment by just loading the center, then this end has to react and induce another moment to oppose it. So this end is rigidly supported. On the other hand, if you look at the other end of the beam, when you look closer, you'll see that it is simply supported, so it has flexibility. It can bend back and forth, and therefore approximately we can consider that the reacting moment here is zero. And that's something that will come in your model. The loading is done by the good old method of using various types of weights, and the weight is this is kind of the holder for the weights. This holder weighs 1 pound, and you can actually add additional weights and therefore increase the weight. For example, this is another pound, so the total will be 2 pounds in here. And you can load it in torsion. For example, if you put it on this side here, then we have 2 pounds multiplied by this arm length, 18.82 centimeters, to give us a torque on that end. And that torque is a pure torque, and therefore the beam is under pure torsion. So this is one method of loading the beam. Another method of loading this beam is to hang the weight right exactly in the center. And when you hang the weight right at the center, that can be considered as a concentrated force, and the concentrated force will produce a moment that is distributed all over the beam. So every point here will have a different moment, including this end. And every point will have a different moment until you get to this end where the moment is considered to be zero. So this location here, we have pure bending. Now we can put one load in the center to give us pure bending, and then we can also take another load and put it to induce torsion. So if we have a situation where we have bending and we also hang this, then we have torsion on the beam, and in addition to bending. This configuration is called combined loading, which we will analyze as well. All right, so let's now talk about the instrumentation on this beam. This beam is instrumented with strain gauges, and the strain gauges are distributed to give us information on torsion and on bending. And you can see that the strain gauges are attached to different points on the beam. This point is marked number 1, and it's for torsion. This is number 2. This is number 3. This is number 4. And this is number 5. Therefore, if you look at the strain gauge on that end, this strain gauge here is a rosette from the top. So it has 3 different strain gauges. The middle one measures the bending, and the 2 at 45 degrees angle are supposed to be for torsion. The same kind of configuration is also on the bottom. So on the bottom we have 3 strain gauges. One of them is parallel to the axis of the tube, and the other 2 are inclined at 45 degrees. So as you can see in the manual, the 45-degree strain gauges, we have 2 on the top and 2 on the bottom. We'll consider those as a full bridge. So you have 4 resistances, and that would constitute a full bridge in the case of using a Wheatstone configuration. And the sensitivity of measurement with a full bridge is about 4 times the sensitivity of measurement for a single strain gauge, which is a quarter bridge. So to summarize, we have 5 quarter bridges here for the strain gauges that measure the bending. This is 1, 2, 3, 4, 5, and the data along this with the strain gauges there for bending will be proportional to the moment at every location. So the moment is proportional to the strain that you measure, and your job is to find the moment distribution and determine the strains in bending, and then compare that to the measurements. And then we have the full bridge, 2 on the top, 2 on the bottom, and that is the strain gauge that is used for torsion measurements, pure torsion measurements. To complete the circuits, especially for the quarter bridge, we use a data acquisition system. And the data acquisition system, you can see it here, is an Acro system. And we have 3 modules. We have a power module that is called Acro 901, so that provides the power. And we have a strain module, 941 and 992 is also strain module. So we take the data here, and then we have an RS-232 connection to the computer, and then we have a program that analyzes the data and give us the microstrains directly. And in that case, we're taking into account the strain gauge factor and the conversion from a change in the value of the resistance to a strain that you can read on the computer. So if you come closer to the computer, you see that it tells us that we have gauge number 1, 2, 3, 4, 5. These are all for bending. And then we have a specific gauge for torsion. That is the one at the end here that's for the full bridge. And we have another column that tells us about the microstrain. And in this column, you can read directly the value of the strain, whether it is for bending or for torsion. There are 2 setups for reading. First one is to zero out the system before you do any experiment. Second one is for read by pushing R on the keyboard. The third one is stop by pushing S on the keyboard, because there's some delay time for data collection and analysis by the software. So the experiment is quite simple, and it is summarized as follows. First, you're going to zero out all of the strains by pushing Z. So when you push Z, it says just a minute getting data. So now it's just a delay time to collecting all the data, and then correcting for the additional inaccuracies in the resistances in the software, so that at the end of that period, we should get here near zeros. And if I read, I'm getting values of minus 0.1, 0.6, minus 0.6, 1.4, 0.2, and 0. So this is close enough to zeros, but you have to consider that in the precision analysis when you do your error analysis of that experiment. So now we are ready to do some measurements. Let's say that we want to do some torsion measurements. And for the torsion measurements, we're going to put 1 pound, which is right here. And it's on the torque arm. And therefore, we don't want to just make it dynamic. So we want to make sure that you do not have any impact on that arm. And once this settles down, then you're going to push the R in here, which is read. And the data is going to be transmitted, collected, and then it will be analyzed by the software. And if you read the software, you see that the level of the microstrains for the bending has not changed very much, except for number 4, strain gauge number 4. You have 4.1 microstrains, which is a little bit on the high side, but that you have to take into account when you do the error analysis. However, the torsion that corresponds to 1 pound is given as minus 27.3 microstrains. And 1 microstrain is 10 to the minus 6 centimeter per centimeter or inch per inch. So now you have done one experiment for torsion. The next is to do an experiment for bending. And for pure bending, as I mentioned, you're going to load the arch in the middle. But before I do that, I have to zero everything again and wait for a while until it is zeroed. And then after that, I can put this load here. This is 1 pound. Let me do a 2 pound load at this point to change. And then a 2 pound load, I can put it in the center arm, and that will give us pure bending. And notice that I have a bending moment along this beam. And once I did that, then I can do a read. And then when I do the read, it should wait for a while, and it will give me a distribution of bending strains all along the tube. And the bending strains, I'm going to read them for you. For gauge number 1, which is right close to the fixed end, it is 48.8 microstrains positive. And then number 2 is 32.2. So right here comes down. So it is high, comes down to here, and then it's going to go down to 0, and then it will flip over. So you see you have minus, for strain gauge number 3, you have minus 41.9, and then 4 is minus 19. And then you go to strain gauge number 5. Theoretically, it should give me very close to 0, but practically it's giving me 6.9. So that's what I would like you to do to analyze the boundary conditions on that end. So I showed you pure torsion, and we showed you pure bending. You're going to repeat the same thing doing combined loading. And the combined loading, we're going to have bending, and we're going to have torsion. So let's say I have 2 pounds in bending, and then I'm going to add 1 pound in torsion. So I have 1T plus 2B. And I can mix this ratio. So I can make 2B, 2T, and 1B, and so forth. So you have this combination that you're going to do according to the manual, and that will essentially complete your measurements.